Good morning. I'm showing 9 o'clock, so we're going to go ahead and get started. My name is Mike DeLacluse, President of Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedules to join us for real-time actionable information using wireless technology. Our speaker today is Lesman's own Bob Kakanda. Throughout Bob's 38-year career, he's been involved in designing and implementing HMI applications, SCADA, PLC, hybrid control systems. After 27 years at Honeywell, Bob joined Lesman as our wireless and controls product specialist. What we plan to accomplish today is to show you the inner workings of ISA 100 wireless. By the end of the session, you should have seen how to implement a system and get data out onto your network and into your existing systems. By the end, we want you to see that it's easier than you think. Just in case you'd like to review the presentation or share with a coworker, the presentation and slide deck will be published on our website in the next couple of days. We will be muting the phone lines. If you have any questions, there's a question tool built into GoToWebinar. Please send me the question and I'll get it answered for you. With that, I'll turn it over to Bob.
Well, good morning again. Thanks for attending. I know you have a very busy schedule, and we'll try to keep this short and sweet and try to keep it moving along. Wanted to again thank you. My name is Bob Kakanda. I'm with Lesman Instruments, and we'll talk about real-time actual information on wireless technology. First question that comes up is, why do we use wireless, industrial wireless? Okay. Well, at the bottom line, to the contrary, it's usually about saving the money. Okay. Saving money means more than just the dollars of the implementation of pulling wires in through the facility. It has to do also with time and the resources that are available. Ran into several applications where the customer says, yeah, it's not a matter of just the cost of pulling the wire, but it has to do with the resources to allocate to get the wires pulled in the first place. If you need all of a sudden we're faced with meeting regulations or EPA regulations, and all of a sudden the instrumentation is not accessible. It's out at a remote facility, and I need to get that back into my control system. So the wireless certainly is a strong alternate solution of getting the data, getting the actionable data information into your system, and it's extremely easy to implement. Where even on startup on wireless systems, it takes a significant amount of time and effort to commission the system, where in the case of wireless applications, it's just amazing that you talk about literally days and hours to get the instrumentation up and running in a wireless application. I want to talk about describing the I/O devices and try to use somewhat of an analogy to current technology that we're all familiar with. And if we look at the individual ISA devices themselves, the I/O devices, I want to relate that and correlate that to an analogy of our cell phones. The I/O device allows you to be able to make the physical connection to the specific application. And you almost want to consider them in relationship to the cell phone, not only just the device, but also the application. So if, for example, I'm running a specific application that's unique to the process on an I/O device, it may be pressure or temperature or flow or level. In your cell phone, it's running a specific dedicated application that allows you to be able to find the restaurant, to find the food source, to be able to use your Google map to be able to find a location. So the I/O device is correlated, or the analogy is literally as simple as the cell phone that we're so familiar with. The next device up in the system that ISA specifies is a routing device, and that literally is our cell towers. That's our routing of wireless signals, okay, to be able to create multiple paths, so that as you're moving around through the system, or you're changing locations, or there's multiple paths for the I/O devices to be able to connect back into the system. So it's in our case, the routers can in fact be a physical routing device that's hardwired into the system, or literally the I/O device can be designated as a router. And these are a self-healing, self-creating mesh network architecture that's built into the ISA 111A standard. The third major component is really the gateway, which you can correlate to actually the cell network, whether it's the cell network that's associated with AT&T or Verizon or Sprint or whatever. But that cell network itself, as we relate it to our gateway, handles the conversion of all the wireless transmission that's being transmitted per the ISA 111A protocol, and converts that back into an Ethernet connection that gets you back into your wired system, back into your control system. It also is a systems manager, a security manager, and a provisioning device, all rolled into that gateway architecture. Okay, just as you can go down to your cell phone provider, they can commission your device over the air. Our I/O devices can be commissioned over the air. So there's a tremendous amount of simple analogy that you can relate between the two. One of the things that is significant that per the ISA 111 device standardization is that you literally have the addition of firewall and additional security, so that you don't have the capability of people jumping in on the network and causing devices to change parameters and so on. So that's built into the gateway systems manager, that a part of the cell network. So again, it manages the communications out to the I/O devices themselves. It handles the security. It also allows you to be able to do the provisioning and the configuration within the system, and then again converting from the wireless communication or wireless protocol back into a wired control system via an Ethernet connection. Okay. The ISA 100. So why have these standards? Right? Why? Right now there's a couple of there's competing standards in the marketplace, but the ISA 100 standard literally was developed by the end user install base to be able to establish an open wireless communication protocol. The analogy there is you wouldn't want to have every cell phone provider to have a different protocol communicating from your cell phone. There's two of them right now, GSA and CDMA standards. One was out of Europe, but that literally allows you to be able to take your cell phone and communicate via the AT&T or Verizon network or whatever, because you have interoperability on your cell phones. Well, the same thing is established per the ISA 111A standard. You have device interoperability. Your cell phone, you can choose to switch from Verizon to Sprint to AT&T, and your cell phone's still going to work because it has an established protocol that puts the communication across the network in the same fashion, the same manner. So the same thing exists with the ISA standard. You have multiple vendors producing instrumentation that runs specific applications that can be interoperable on the network. You can mix and match vendors' hardware or application or I/O devices within the architecture. The devices are, the standard allows you to be able to support both routing devices and non-routing devices. The distinguishing factor there is, can I build a sub-network mesh architecture if I need to get to remote devices? So both technologies, both topologies are supported, both mesh and star-type topologies. This enables you to have tremendous flexibility and it truly a deterministic network, since all of the devices are managed through the systems manager and have their own communication transmit receive time slots. So it's not a random haphazard communication. It literally is designated and managed. All the communication across the wireless network is managed by the systems manager, giving you predictable performance and also the capability of establishing redundant paths on communication in a truly deterministic meshing network architecture. The significant advantage there is you literally have the ability to establish the communication in essentially a wired equivalent network, but now I'm doing it wirelessly. So update rates of once per second are achievable. Latency times in the order of 100 milliseconds are established per the ISA standard. The system, because you need to be able to establish the standard, also has to be tolerant to other communication protocols. Just because we started off with you're putting in an ISA 111A network for your wireless instrumentation, you may have already established Wi-Fi communication to existing, to other processes within your facilities, whether they're literally involved in inventory management or you've got standard 802.11. We have to be, the ISA standard says that it has to be tolerant, it has to be able to coexist with existing Wi-Fi architectures that may already be within your facility. The standard also establishes multiple communication protocols over the same wireless network. Okay, all we're saying is that there may be multiple. The analogy here is that I may have a cell phone that it doesn't matter the communication language that the person is talking over. One can be speaking in Spanish, the other one's talking in French, the other one's talking in German, but I need to be able to support all of those protocols or communication protocols within the architecture. The ISA 100 standard devices that we supports Profibus, supports HART communications, supports foundation field bus communications, besides and over and above the standard 111A protocol. So multiple languages can be transmitted over the Wi-Fi system, or not the Wi-Fi system, but on the ISA 111A system. It also incorporates all the data security that you'd ever wanted, so you can't get rogue people coming in and disrupting your system. It has built-in encryption in the device on all of the data that's being transmitted. It has message authenticity so that it knows that it's talking to the right device at the right time, and time security is key. So there's only a very, very small window for each of the device in the order of milliseconds to where the device actually turns on and communicates, and the systems manager and the device knows when it's supposed to turn on and when it's supposed to receive data. So you can't just come into the system and provide a rogue information. It also has a firewall built into the system architecture, so data is intended to come from the wireless system into your control system, and information from the control system can't be going down and communicating into the wireless architecture. Also, the standard establishes real-time key distribution. So not only do you have over-the-air commissioning of devices when you're starting up the system for simplicity, you also can set up the system to automatically change security keys. So you're literally reducing cost, risks, and the time reduction to be able to keep the system totally secure and operational. Let's talk about some of the key components. In this case, I'm going to take us over to the product lines that we happen to support, that supports the ISA standard, namely the Honeywell XWire 6000 system that we have implemented and currently that is in compliance with the ISA 100 standard. We talk about the field instruments. These are battery-powered wireless field instruments, capability of once per second update rates with battery life capability of up to 10 years, depending upon its functionality and its update rate, and whether it's a routing or non-routing device. Off-the-shelf battery, D-size, lithiums, and these instruments are intended, or we can say instruments or applications, right, of the individual devices are intended to be in Class 1 or can be Class 1, Div 1, IP66 environments. So I can put them into an explosion-proof environment. I intended to mount them outdoors so they can survive the weather. The devices themselves, again, with multi-year battery updates with the capability of even once per second update rates. And I can have distances of 1,000 feet between the instrument, the field instrument itself, and the access point or a router. We kind of use those interchangeably in the system. And that's with a standard 2 dB antenna. All of the instruments that are supplied in the XWire 6000 and in many of our competitive, and I don't want to say competitive, on the other instrument suppliers, Yokogawa and so on, also have the capability of changing the antennas so that you can get additional distances. The other key component is the field device access point in the center of our screen here. This is an access point. It's a routing device also. Allows you to be able to build a self-healing, self-meshing ISA 111A network. It is, again, the access points for the instruments. It comes with a dual antenna technology that allows you to be able to provide you with diversity. So it runs through an algorithm and it looks for reflected signals. So there may be a signal that's bounced off of one piece of metal or another device. The dual antenna diversity allows you to be able to, and the algorithm running inside the architecture allows it to distinguish between the primary signal and a secondary reflected signal. Again, it is also a Class 1 Div 1 device, IP66. It's intended to be mounted outdoors, so it's not, or obviously you can put it indoors. And you have the capability of having 60 field instruments or 60 different applications with multiple inputs tied directly into an individual field device access point. The heart of the system is the wireless device manager, and it is the security manager. It is the configuration tool. It is literally the device that connects and converts the wireless signal from the ISA 111A standard protocol and transfers that information back into your process control network. That process control network may have its own particular language or communication standard that it wants to adhere to. That may be HART, it may be OPC, it may be CDA, which is Control Data Access. It could be GCI, which is a general system interface. And all of those protocols to communicating back into the host system is fully supported within the systems manager. It also is the security manager. It has an integrated firewall, which we mentioned earlier, that it doesn't allow data transmission to be from the process control system or intrusions or interruptions to change device parameters or, for example, outputs. You can't communicate, can't get rogue signals back through the system. So there's a built-in firewall. And again, all integrated into the systems manager. Wanted to give you a little bit of the performance capacity, in particular, of the XWire 6000, Honeywell supported architecture. And in this case, we've got those FDAPs, or powered backbone routers. And in our configuration right now, the capacity is that you can have up to 40 backbone routers or access points in the system. Now, if you have routing devices, because now you can have actual instrumentation, right? A transmitter itself could also be a router. It maintains the same routing, number of routers that's supported in the system, both backbone routers and instrumentation routers, is still 40. We said earlier that you can have up to 100, we can have, I think there was 60 devices per access point as a limitation. The total system right now supports 100 field instruments communicating into the ISA 100 network or through the wireless device manager. That limitation is based upon time, security management, and all of the overhead that it takes to make sure that we have a reliable and secure network, updated in time-slotted allocations across the architecture. The number of field devices connected to an access point at a once per second update rate, 18. We talked about the 60 at a 5-second update rate. Now, when you turn an instrument into an access point, which you have the capability of doing because it's building you literally can build a mesh network out of the instruments themselves, you now have 10 devices at a once per second, or one device at 1 per second publish rate, or if you are taking it back to a powered access point, you can have 10 devices at a once per second update rate. And then 40 at a 5 per second or greater publish rate. So again, you need to look at, again, because they're all time slotted, they're all going to be accessing battery power in a instrument. You can have, if you're going at a once per second update rate on using a instrument as a router, you have some limitations that are going to limit you there. But if you can take it up to a powered router, you can get 10 devices at a once per second update rate. Okay. It always comes up and says, well, how far can these instruments be apart? And this one just kind of gives you a clear map. This one happens to be utilizing almost all of the antenna types or 2 dB antennas. And from the access point or an FDAP, you can get 1,000 feet between the transmitters. You can obviously see that if I change the antenna type to a 4 dB antenna, and we have the capability of changing those to directional antennas to even get further distances out on the instruments, and they're field upgradable. We've got a couple of applications where we have upgraded them in the field because of restrictions or device equipment that was in the way, where we had to get the antennas themselves over and above particular instrumentation. You also have the capability of, again, we said the instruments themselves being functioning as a router, in this case where we had the particular transmitter that was functioning as a router talking to a secondary transmitter. With the standard 2 dB antennas, you've got about 500 feet of line of sight communications to maintain the distance. Also down at the bottom here, you'll notice that there's a HART transmitter with what we call our OneWireless adapter, and that allows you to be able to take HART wired transmitters and automatically convert that into the ISA 100 standard protocol communication. And again, that particular device has its own battery-powered radio built into the system, communicating per the ISA 100 standard, and you've got about 560 feet of distance between that device and other devices. So if we look at how the Honeywell's implemented the OneWireless architecture, as we said, there was 3 major key components, right? We had our systems security manager, our configuration tool. That is the wireless device manager. It's all built into that device. At this point, I'm Ethernet out. I'm going back into my control system via a chosen protocol or chosen communication. But down from here, I'm on my field device network. Okay, I wire into an FDAP, and I need to have at least one connection to an FDAP, and then the FDAP then communicates out to my individual applications or individual sensors out in the wireless realm. I can again have routing devices, okay, to function as a access point. So this one's an access point for that transmitter, okay. Or I can have direct communication to a powered access point. Literally, you can get into a very sophisticated, redundant application where I can literally have the capability of running redundant systems managers, redundant powered field device access points with meshed access points in the architecture, and then the instrumentation literally will build its own redundant paths of communications going from a particular transmitters to an access point back up to both powered access points in the system. So I can always, the system will automatically try to build redundant wireless communication paths down at the instrumentation level with powered routers. Okay, you have redundant communication paths. These two happen to be outliers. We don't see redundant communication paths down there. And I literally can have redundant systems managers to ensure a complete redundant capability in the architecture. So again, I can go from the simplest type of architecture solution all the way up to a completely redundant wireless system and not impact the performance of the architecture. The implementation back at the Wireless Device Manager is a web-based tool. So literally I establish a web-based interface in through the Systems Manager or Wireless Device Manager. The Wireless Device Manager has a whole set of tools that allow me to be able to do configuration, and I'll go live and I'll show you the tool and the implementation of the multiple protocols and how to get the data out of this from these wireless devices back in the control system utilizing the tool and the resources. But in this case, you'll notice it has the capability of providing monitoring to monitor all the alarms and events, and you have through the configuration I can set up alarms. It'll create reports for me automatically through the web-based interface and the configuration tool, and it allows me to be able to do individual configuration down at the instrument level to set up the process variable parameters, the scaling, the range, the update rate, the publish rate. So all of the functionality of the system is configured through the web-based interface. This one's a kind of a busy network, but in this case, we didn't pull out the individual instrumentation. But you'll notice that in this case, back from the WDM, we've got a couple of powered access points, namely this one and that one that's tied in the architecture, and then we have a routing access point. And then you'll notice that you'll see multiple paths or multiple points back into the access point. None of that configuration is done manually. That's all done through the systems architecture. It finds the best communication path and establishes if I have multiple access points within the systems or devices that are allowed to be routers. So remember we said our instrumentation can also be routing devices. If I turn on that capability, it'll try to establish, and if it's available, it'll try to establish redundant communication paths back into the access point that gets tied back into the systems manager. Now, all of the time slotting, the communication, the security, the protocol, that's all taken care of back at the wireless device manager. Okay, so it's taking care of all the time slotting, all of the routing, all of the networking, and it determines the ideal solution that needs to be implemented through the wireless architecture. Okay. So once the data is back at the device manager, in the Honeywell solution, it's the wireless device manager. It now needs to establish, I need to get that data out of there. I've got all this wireless data coming back. I need to get this back into my control system, and I need to have it communicated in a fashion that my control system can easily get that data. Whether I'm talking to a PLC or whether I'm talking to a distributed control system or whether I'm talking to a historian, okay, to be able to collect the data, I need to be able to get that data out of that WDM, the wireless device manager, via the Ethernet connection, and I need to either connect via OPC or MODBUS or HART, okay, and get it back into my control system. And if it needs to be able to provide it via RS-232 or 485, that's also supported out of the WDM. Okay. So we talked about these protocols that we need to get back into the control system. If it's a MODBUS interface, literally I will select my WDN, I will click on my MODBUS selection on the communication, and I'll show you this on the real-time connection of the device. I need to enable the MODBUS communication protocol within the device manager. I need to establish what communication port it's going to connect into and the baud rate that I'm going to communicate to. I'm going to set up my byte order. Okay, so for people who have fooled around with MODBUS communication, obviously there's big Indian and little Indian, and then I need to be able to then utilize the data, okay, that's now wireless and put it into coils and register locations that can be accessed from my control system or my PLC, okay, or my historian running up at the control system application. I'm pointing this one out because you don't even have to worry about the syntax, which is always a classical pain in the butt, okay, candidly, of trying to remember what the syntax was for the temperature transmitter and whether it's PV, and literally point picker in the wireless device manager allows you to be able to scan through your devices, okay. It pulls up the device that you're looking for, and if you want the process variable, you click on the process variable, you copy it, and you paste it into your register data. So you don't even have to worry about typing the information in. It'll select through point picker in the WDM and build your register information on the individual process variables that's coming from your instrumentation or your application data. Okay. So in this case, if I have a system that wants not MODBUS but wants to communicate the data via HART, so for example, if I'm running into an Emerson Delta V and it wants the data to be looked like HART instrumentation coming in, I would select the HART protocol within the WDM. I would go to point clicker, and in this case I happen to have Honeywell instrumentation that generates HART data, and I literally have point pickers say I want the individual transmitter, it gives me my manufacturer ID, it gives me essentially the DD or the device descriptor data coming off that instrument, so that when I'm connected via the communication port, let it be 232, 485, or Ethernet, the HART data now is actionable back at the control system because it knows the device descriptor level and it knows what the primary and secondary and tertiary process variables are that's associated with the data that's coming in off the wireless architecture. So that would be the HART data. Now my preference is OPC because I don't like to have to remember all of that information to configure the data back into my control system. OPC literally says, back at my wireless device manager, I select OPC, I enable it, and now it takes all of that wireless information that's out on that network and it makes it available to a OPC UA client or DA client. Okay. And I'm going to demonstrate that here shortly. You'll notice, again, this is done through the wireless device manager operator interface. You'll notice that it's a standard IP address to interface, HTML interface, so it's 192.168.130 or whatever I change it to establish the interface. Okay. So what we're talking about in this case, and again I'll demonstrate OPC, I literally have my, as a simple network from my wireless device manager communicating out to my wireless field device network. Okay, so I have data coming from all of the instrumentation, and now I need to get back into my network architecture, back into my control system, so I can display, collect data, provide reports, historian back at my control system. That may be Wonderware running an OPC client. It may be an Allen Bradley RS view system or an R control system. It can be, could be Emerson's Delta V control system with data coming back even via OPC, and they support OPC. So I can literally collect the data, provide that in the architecture. At this point in time, I'm going to transition over to a online real-time system that I happen to have configured that is running. Okay. And in this case, you'll notice we have the Lesman Wireless Device Manager, okay, which is the systems manager. It has the multiple communication protocols. Okay. I'll show you that we did select OPC. I have my access point, which is my powered router, and it's communicating out to a couple of transmitters. I've got one here that Mike is changing the pressure on by pressing the bulb, and we'll look at its capabilities here in a second, and I'll show you how to configure it. And then I've got a universal transmitter that has 3 inputs on it. You know, a lot of the transmitters have multiple inputs or an output configured on the device. So looking at the tool itself, obviously one of the things that I wanted to make sure of, okay, is when I looked at and I've got a configuration capability over here. So when I configure it, I can configure the interface, okay, and since I clicked on OPC, you'll notice that I have him enabled, okay, because I want to transmit this information back to my control system via OPC and run it back into a UA, Universal Access Client, and see what kind of data I can get out of it. I'm going to take you down a little bit farther into the instrumentation level, and I can click on my device. You'll notice that when I look at my device, it tells me who it's communicating to. It tells me the signal quality of the device. It tells me the RSI, the signal strength of the device, okay? And that is presented through the web interface all the time, and it gives me an overall status. If I go down to the individual device itself, I can now set up the transmission, the publication rates. I can set it up as a routing device or a non-routing device. I can do the channel configuration. Okay, I can tell it what's on whether I'm enabling or allowing all of the multiple channels to be configured. If I get down into the individual channels themselves, you'll notice that I just pulled out a few of the configuration tools. We have channel summary, process variables, the mode, the scale. I can calibrate the transmitters right from this particular tool through the configuration tool. I can configure the type of sensor that I'm connecting to the device just by picking the device. In this case, I've got type J's. I can set up my scale and range, so I may not want to look at, if I look at the entire the scale of the device. Okay. In this case, you'll notice that the particular the thermocouple set up from -18 to 871 degrees, and I set it up for F with 2 decimal places, but I can certainly go through and change the scale. So I may want it to look as, the scale only go from, let's say, 100 to 400 degrees. So I may want additional resolution. The tool itself also gives you the capability to monitor the trend of the individual device. So in this case, there's our particular trend. Mike has cooled it down, and it's cooling down. He grabbed it earlier. And in this case, if I looked at the trend of the second transmitter that happens to be on that universal device. Okay. Or I can click over on my individual pressure, and Mike was changing pressures on our 0 to 400-inch pressure transmitter. Okay. So this was in particular is the instrumentation interface. You'll notice that across the I want to move. It's moving me. I want to get to the. I want to go top.
You're still
okay.
It's okay.
Okay, but I wanted to be able to show you the tools across the top.
You gotta use your slider bar.
Oh, there we go. Here we go. Across the top of the slider bars is literally all the tools we talked about. In this case, we're in the monitoring mode, so I have the capability to set up what's being monitored. You have the capability to put a background in, so I can actually take this out and put it out in the real. Put a photograph or a bitmap within the application. I can monitor my alarms and events. I can get my reports out of the system. You'll notice that I can select the devices that I want to display. It has the capability to provision new devices in the system over the air. So if I bring in a new device, I can activate it. You'll notice we had point picker capability, showed you that earlier. Okay. All of the upgrades, okay, or changes in the system is done over the air. It's done via this tool, okay, and I can upgrade my applications. And then do all of my configuration. Okay. Now, one of the things I wanted to show you, obviously, we enabled our particular devices to go over to OPC. In this case, I have a particular application. It happens to be Unified Automation UA Expert. It's a thin client. So I'm simulating my PC being a host computer. Okay. And in this case, you'll notice all I did in my application was establish the connection via OPC, and then I clicked on my Lesman R220 demo unit, and down here at the bottom of all the address spaces are all of the tags that were automatically made available for me from the system. So I had my transmitter, I have my battery, in this case on my pressure transmitter, I had a battery life. In this case, all I did, I'll take out the battery life here, remove him, and then we'll put him back in. So if you wanted, for example, to have battery life to be monitored by the control system, I would literally grab this guy's %, drag him over, and that literally now is available in my process control system because this client is running on the process control system. So that data is now available. Okay. Eliminating, just taking him off, delete, remove, selected node. Okay. The same thing would apply. Let me go down to, for example, I can show you the temperature transmitters. So all of these parameters, the statistics, the analysis, the alarms, okay, are all available for you in from the OPC client. Okay, so let me go put our % from the battery transmit, make him available back into my control system. So in this case, I've got a battery life of 79%. I've got 1.73 years left on the batteries. And what I did is when I was trying to get my process variables, I came down, clicked on my process variables. It literally now made it available into the control system. So as you can see, with OPC, my preference, okay, all of the data is available to you. I can get the sensor type, the thermocup, the TC resistance. I can get the cold junction temperatures. I can get all of the data associated with any of the alarms and events in the system and literally make that available within the control system. And you'll notice I did little to no configuration. I let OPC come over there, grab the data, make it available to me, and now I select that, grab that information, and tie it into my control system because I'm running, in this case, a UA expert client, okay, that makes that data available that I'm going to be running on the process control system. Okay. I'm going to take you back over to the presentation here, and I'm going to kind of move towards the end, but I want to talk about there are two wireless standards in the marketplace. Okay, there's the ISA 111A standard, and then there's HART wireless. Well, there are some significant differences. The architecture on the ISA 100 standard is built on a backbone architecture because it's intended to have a 100 millisecond latency time. It is supposed to support wired equivalent capability for increased signal quality, minimum latency, and quality of service. The gateways on the wireless, on the HART wireless side, are for do not tie into a defined network architecture. They build their own mesh network architecture, and however it gets built by the system, whatever it gets fined, down it goes in the way it gets built in the architecture. Where in the ISA 100, it's a defined, time-stamped architecture. It supports The ISA 100 network supports multiple communication protocols. It allows multiple people to talk with different languages over that wireless architecture, okay, from the cell phone's analogy. The HART wireless system only supports HART via the thumb drive. So you can handle Profibus, HART, you can handle Foundation Field Bus and transmit that over the ISA architecture and get that back into the control system. The field instrumentation on the ISA 100 use off-the-shelf battery. Our friends at HART do not. They're proprietary batteries. Subsequently, the cost is significantly higher. The devices in the ISA 111A standard allows you to determine whether or not the device is a routing device. And obviously, if I can take it back into a powered router and not have a transmitter be a routing device, I can extend battery life capability. On the HART system, they're inherently all routing devices, which means they're doing additional transmission even though they could have gotten back to their gateway or their access point. It typically will go through their transmitters to find a path back. So you can choose whether it's a routing device or a non-routing device within the ISA 100 standard. The Honeywell OneWireless system allows you to be able to have, combines meshing with routing radios, okay? And on the Emerson system, it's a meshing with limited redundancy capability, where you have full redundancy capability that you can build into the Honeywell OneWireless system. The standard radio power on the Honeywell transmitters is a 16 dB transmitter. The radio power, and it's adjustable, so you can change it. On the OneWireless system on Emerson, it's fixed at 10 dB. So you do lose some transmission distance because you're transmitting at less power. The field instruments use off-the-shelf, on the Honeywell version use off-the-shelf batteries, and the Emerson uses proprietary batteries. Control-ready performance with 1 per second update rate on the Honeywell OneWireless system. The update rates are limited to 4 seconds, and you can get 1 per second updates if you're the first transmitter off the Emerson gateway. That is the limitation. In our case, you can have multiple devices tied back to the powered routers with a once per second update rate if that's what's required. Okay. Want to talk about the applications, right? Since your cell phones have multiple application capabilities, one's going to be able to, as I said, find your location. The other one's going to find out where you want to go eat. One's going to run your investment analysis software. Well, there's a whole bunch of instruments that literally are your application devices. So within the OneWireless system, the XR6000, Honeywell provides pressure, gauge pressure, allows you to be able to do the flow, the level, the temperature, multiple inputs per transmitters, so I can have multiple thermocouples or multiple RTDs into an individual wireless transmitters. I can have them directly into thermal wells, or I can wire my RTDs or thermocouples directly into the device. I have an application tool that allows me able to bring in anybody's 4 to 20 milliamp, 1 to 5 volts. So I've now got a specialty instrument. I've got an analyzer that I want to be able to get the data back in wirelessly to the other side of into my process control system, and it provides me a 1 to 5 or a 4 to 20 milliamp input. I can wire that wired specialty transmitter into my wired device, from my wired device into a 4 to 20 milliamp universal transmitter, and transmit that information wirelessly. There's a FlexLine radar system that's available from that's ISA 108 compatible. It basically allows me to do custody transfer, tank gauging systems. Honeywell SKF has worked with Honeywell in developing the vibration transmitters, which allows me to be able to put on 2 vibration transmitters, both on, let's say, a pump and fan motor system. Allows me also to measure temperatures and to be able to get my vibration analysis, my envelopes, okay, and allows me to be able to do fast Fourier transfer of data via the OneWireless architecture back into the SKF system. So again, another application or another app note that's available. Okay. Simple valve positioner. I can clamp my device onto a valve, and I can monitor the position of the rotation with different linkages. And then we also talked earlier about a device called, in our case, the thumb. We call ours the finger. Okay. And in this case, this allows me to take wired devices, Honeywell, Emerson, Yokogawa, anybody's wired transmitter, and to be able to tap off and collect the HART data, okay, so I can get digital signals off of the wired transmitter and transmit it wirelessly back into my control system, so I do not have to run the wired system. So I think that kind of wraps up where we're at. Hopefully that meets the expectation that Mike set for us here.
It does. If any of you have any questions, please feel free to use the chat tool, because I'm not showing any questions at this point. So, Bob, you must have done a good job of explaining it. While we're wrapping up here, feel free to type a question in. Again, Bob, thank you very much for your presentation. If there are any specific application questions, feel free to call us at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, feel free to ask for myself or Bob, and we'll make sure that you get taken care of. You can also send us an email. My email is miked@lesman.com, and Bob's is bobk@lesman.com. We are constantly looking for ideas for other webinar topics. If you have a topic that you'd like presented, or a how-to that you'd like presented, please feel free to drop me an email. At this point, I still don't have any other questions, so we will, oh, one just popped up. Can you give me some additional instrumentation examples? Think furnaces, maybe. A really good one on furnaces that we've done is specifically rotating kilns. And it's not specifically a furnace, but it is a heat application. where the transmitter got mounted to the rotating kiln, where the wiring piece was just not as straightforward as you'd like it to be. And to my knowledge, that thing's worked for quite a few years.
For example, I know of several where talk about furnaces. The one that, when you said furnace, the one that jumped out to me was an arc furnace application that we did down in the Alabama area, and literally we're monitoring the temperatures on the outside of the arc furnace. The reason for putting wireless in there is to be able to eliminate the extensions of the thermocouple wires. That may be applicable to your application also, whether you're monitoring the extensions of thermocouple wires that are, in this case on the arc furnace, were getting destroyed, the arc furnace in the application, so they were able to do that wirelessly. But whether you're monitoring drum level, whether you're looking at overpressure, secondary temperatures on the furnace, whether you're monitoring it from thermocouples or RTDs, whether you're looking at steam flow, I certainly could look at a wired or a powered flow meter and convert that signal wirelessly. Again, you know, there's a trade-off. If I already have wired instrumentation that's pulling off the application for flow level, drum level, water level consumption, then it may not provide the cost-effective solution for you. But if it's not the case, where you're adding instrumentation into the furnace, or I'm trying to decrease the amount of maintenance that has to be done because I'm losing instrumentation because of sensor failures or my sensor runs, now I can get a device where I can eliminate the elongation, put my transmitter as close as I can to the device itself. And these are industrial transmitters, so they're intended to survive in a wide application of temperature environments.
All right, the next question we have is, how do you calibrate a pressure transmitter from your desk?
Well, the good news is the transmitters themselves do not need a significantly large update in calibration themselves. Right now, the transmitters, the recommended calibration is somewhere in the range of like 3 years before Honeywell recommends that you provide the calibration. But you're absolutely right. I certainly can take my user interface via the wireless transmitter. If I am going to calibrate it, I'm going to have to put in a pressure source on the device. I'm going to have to set my zero, my full scale, and I'll have to do the calibration by providing a calibrated pressure source on the transmitter. Now, the good news is, if I can remove it from my head, because I don't have the only connection I have is if I can disconnect it. If I've got a manifold on the device, I can disconnect it, bring it into an environment that I can in fact calibrate it, and go into my instrument shop and connect into the system and provide the pressure head there, because I don't have to disconnect any wiring. Okay, all I have is the 3-valve manifold or the 5-valve manifold on the pressure connection, and away you go. I can shut those guys off, unbolt it, and calibrate my transmitter in my instrument shop.
And get access to the data through a web browser.
And still get the all the data.
You can watch the transmitter through the web browser,
right,
and make sure that it's all being done right.
Right. I hope that answers the question.
Yeah. I don't have any further questions. Again, if you do have questions, feel free to. Oh, another one popped up.
Oh, I guess we're going down the right path.
All right. Let's see. Carburizing furnaces about gas percent and carbon levels. Temps inside per zone 5. Well, I think the way you'd have to pull that back is
4 to 20 milliamp off that transmitter.
Or if it's in the case of like a Honeywell Analytics, some of that is HART enabled, so you could hook that up HART and get more of the variables back. So if those gas detectors are HART enabled, you could pull it back that way. Otherwise, you could pull it back for using the 4 to 20 into the
universal
transmitter.
Yeah.
Let's see. Also,
most of the percent carbon transmitters are 4 to 20 out, so I would grab that information on percent carbon back into the universal wireless transmitter, and then I don't have to. I could put it in parallel or put it in the loop and add it into the control system over and above the control loop for carbonization.
Okay. To continue the question, we have temps inside per zone, and it's 5 thermocouples, are easily connected. So for historical data, how would we interface and store that? I think historical data would be relatively easy. You're going to pull an OPC into some sort of data historian, and we can set you up with an inexpensive data historian, starting with the Matricon at what are those, $800 or something. They're not very expensive.
Right.
All the way through to something that is fairly complicated and could take tens of thousands of points, but it's really all application driven, and we could certainly get with you and review the application and make sure that system we put in place isn't overkill and would last for a significant period of time.
Right. I think Mike addressed it. I mean, from the simplest application, a wireless transmitter could handle 3 thermocouples per transmitter, so you're not looking at multiple transmitters to collect your devices. And you said you had 5, so I would need 2 wireless transmitters. And at the most simplest application, I could have done it in to Matricon, as Mike mentioned, an OPC historian that'll take it into Excel. I could then take it. The next step up from there would be a video recorder. Okay, you can now have a video recorded historian, because video recorders are more like historians than just a recorder anymore, or moving up to the next level and getting it back into the process control system, whether it's available. I mean, and there are several HMIs available either through Honeywell or through the system that you already have, or whether it's just tying it back into your historian that's tied into your control system, which may be Pi or whatever. I hope that kind of answers the question.
Yeah. The last part of this question I absolutely love is we have a terrible environment, extremely dirty. Think coal mine.
Do you?
Yeah. I don't. These things are used to being in these environments. They're used to being filthy dirty. I don't see any issue with any of it.
No.
Short of sending the thing into super high temperatures that, where you're going to melt electronics, I think you're safe. The next question that popped up is, which historians do you suggest? Again, we talked a little bit about that. We could go all the way from the low end being a Matricon OPC historian starting at about $800 that brings your data into Excel, all the way up to, we now have access to Honeywell's Experian,
distributed control,
which is a distributed control and can take up to tens of thousands of points. So we could go from something that is very simple to implement to something that is relatively complex and into everything in between. So we can take care of it. It's just a question of talking through the application, making sure that we get you what you think fits your future needs. Those are all the questions we have. Again, thank you all very much for attending. We will be publishing this webinar so that you can share it with your coworkers. If you have any questions, feel free to contact Bob or I. Thank you very much. Have a good day.
Thanks, guys.